Lesson 3, Chapter 3, we're going to be looking at the definition of a mole and then using moles and Avogadro's number to do some calculations. We're also going to explore stoichiometry and chemical equations. First, we're going to start by talking about the mole. So what exactly is a mole? Well, if you remember back from Chapter 1, and we were talking about physical quantities and SI units, the mole was actually the SI unit for the amount of a substance. Mole was actually devised by chemists so that they could count chemical particles simply by weighing them. So how exactly do they do that? Well, first off, they define the mole by using Avogadro's number. So Avogadro's number is 6.022 times 10 to the 23rd. So they define the mole by saying 1 mole is equal to 6.022 times 10 to the 23rd particles. Now, that word particles can actually stand for multiple entities. So what I mean by that is you can replace the word particles and put atoms, or molecules, or formula units. So in that case, we can say that 1 mole of a substance is equal to 6.022 times 10 to the 23rd atoms, for instance. Now looking at that number, 6.022 times 10 to the 23rd, that's actually a very, very large number. It's in scientific notation, so if we were to represent it in normal notation, we would have to move the decimal point 23 times to the right, making this number extremely large. I don't even know how large. It's more than trillions. It's like gagillions or something ridiculous. So how are we going to use this definition? Well, we're going to use it very similar that you would use the definition of a dozen. So if you know, 1 dozen is usually equal to 12 of something. Now, just like 1 mole is equal to 6.022 times 10 to the 23rd particles, 1 dozen is equal to 12 units of something. So we can replace that word units with multiple things, right? We can say a dozen pencils, and we're talking about 12 pencils, or a dozen donuts, more common, right? You're talking about 12 donuts. So it can be used for multiple different conversions. And the reason I'm saying conversions is because you'll notice both of these, the mole and the dozen, have an equal sign saying what it's equal to. Whenever you have two numbers equal to each other with different units, they can be used as conversion factors. So when we are using moles in calculations, we're going to be using the definition of a mole to solve for it. The definition of a mole being Avogadro's number. So we're going to calculate it the same way that you would use the definition of the word dozen. So let's start by looking at the first example. So the first example asks, how many eggs are in 3 dozen? So the term entities in the definition dozen is going to be eggs in this case. So how would you solve it? Well, you take the number 3 and you multiply it by what the word dozen stands for, and it stands for 12. So 3 times 12, you get 36 eggs. So you're going to do the same thing with the word moles. So if you were asked, for instance, how many atoms are there in 3 moles of a substance, you would take the number 3 and you would multiply it by what the word moles means. In this case, the word moles means 6.022 times 10 to the 23rd. So when you multiply that out, you get 1.807 times 10 to the 24th atoms. Now keep in mind, I'm just showing these as examples on how to do the calculations. I am not keeping with significant figures here. So when we are talking about moles, the entities that it is equal to after the 6.022 times 10 to the 23rd, it can be atoms, just like we saw in the previous example, or it might be molecules, formula units, ions even. So the word entities can be replaced with a multitude of things so that we can calculate a multitude of chemistry-related problems. So Avogadro's number, you'll see in future equations, is often represented with this letter n sub a. Now, when we're talking about 1 mole equaling 6.022 times 10 to the 23rd of something, as we saw in the previous slide, it can be 10 to the 23rd of atoms, elements, ions, photons, right? There's a multitude of things we can calculate. So how do you know which entity or term is being used? That's what this table here is for. If we're talking about 1 mole of an element, for instance, so an element off of the periodic table, then we're talking about 6.022 times 10 to the 23rd atoms. It does not matter what element we're referring to. So if I say 1 mole of oxygen, well, in 1 mole of oxygen, there is 6.022 times 10 to the 23rd atoms of oxygen in 1 mole. If I'm talking about mercury, there are 6.022 times 10 to the 23rd atoms of mercury in 1 mole. Looking at covalent compounds, which we learned about in Chapter 2. So if we're talking about covalent compounds, the term used is molecules. If we're talking about ionic compounds, the term used is formula units. We'll get into photons in later chapters. So let's try an example calculation problem. If we were asked how many moles are in 9.6 times 10 to the 24th molecules of oxygen. So how would we solve that? Well, we would have to do our railroad tracks that we learned in dimensional analysis. It's going to be the same type of calculation, just using the conversion factor where 1 mole is equal to 6.022 times 10 to the 23rd. And in this case, it's 10 to the 23rd molecules is the entity being used. So to solve for this, we would want to start our railroad tracks in that upper left-hand corner with the number given to us in the problem. We then take the conversion factor where 1 mole of oxygen is equal to 6.022 times 10 to the 23rd molecules. Notice we're putting the Avogadro's number, which is attached to the entity molecules, in the denominator so that molecules and molecules cancel out, giving us an answer with just moles. Now in this problem, we are looking at sig figs. So you'll notice in the original problem, if we look before the multiplication sign, there was 2 significant figures. So we want to make sure to report our answer to 2 significant figures. So that's why we rounded it up here to 16. Next, we're going to look at calculating molar mass. Now, molar mass is oftentimes referred to as molecular weight as well, so those 2 terms are interchangeable in this course. So what is molar mass? Well, molar mass of an element is the same thing as the atomic mass on the periodic table. So you can see this little cutout of carbon from the periodic table at the very bottom of the slide. So the atomic mass, the average atomic mass that's written there, that is the molar mass of carbon element. Just 1 atom of carbon. Now, we're going to learn how to calculate the molar mass for compounds, so where there's more than 1 atom present. So in order to do that, we need to sum the atomic masses of all the atoms present in the chemical formula. So in order to calculate, we of course need the chemical formula itself. Some examples are shown here for water, copper 2 chloride, and that's benzene. Remember with chemical formulas, the subscripts give the number of each atom present. So the subscripts being the numbers that come after each atom. So in the case of hydrogen, there's 2. Oxygen, since there is no number present, it would just be 1. The other piece of information you need in order to calculate molar mass is the atomic masses of each element that are represented on the periodic table. So let's look at an example. We're going to look at calculating molar mass for CHCl3. So how do we do this? Well, for each element present in that chemical formula, we want to take the number of atoms present by looking at the subscripts after each element and multiplying it by the atomic mass of that element, and we find that on the periodic table. Once we're done doing that for each element, we're going to add the molar masses of the elements together and then put units of grams per mole. Now the units of grams per mole is very important because this is going to be extremely useful to us later when we're doing conversions between grams and moles. Because since there are 2 units present, grams and moles, we can use it as a conversion factor to get between grams and moles. So let's look at the example. The chemical formula of CHCl3 is shown here. So we like to make a table with all the elements present: carbon, hydrogen, chlorine. So for carbon, looking at the chemical formula, there is no subscript after carbon, so we assume there's just one carbon atom present. We then multiply that by the molar mass of carbon that we find on the periodic table, which is 12.01. Moving to hydrogen, looking at the chemical formula once again, we see there's only one hydrogen atom present in CHCl3. So we multiply that by the molar mass of hydrogen found on the periodic table, which is 1.008. Moving on to chlorine. There is a subscript after chlorine, and the subscript is 3, telling us there are 3 chlorine atoms present. So we multiply that by the mass of chlorine found on the periodic table, which is 35.45. Multiply across and add all the 3 values together, and we get a total molecular mass of 119.37, units being grams per mole. Let's look at some practice problems. Feel free to pause and try these on your own to check your answers. For molar mass, or molecular weight of silicon, so number 1 here, notice this is not a chemical formula. This is an element by itself. So this is the easiest question you will get referring to molar mass. All you need to do is find silicon on the periodic table and find what its mass is and report it with units of grams per mole. So finding silicon on the periodic table, we see that its mass is 28.086. So its molar mass that we would report is going to be, sorry, I'm having technical difficulties, 28.086 grams per mole. And they just wrote it in a conversion factor fraction form. Now, next problem is the molar weight. I should say molar mass or molecular weight, but little glitch there, of HClO3. So for this one, there is a chemical formula. So you need to go through the steps of multiplying how many atoms there are of hydrogen by the mass of hydrogen, how many atoms there are of chlorine times the mass of chlorine, how many atoms there are of oxygen times the mass of oxygen on the periodic table, and then adding all those values together. So here we're showing how that works. So there was one hydrogen atom, so we multiply that by its mass. Chlorine, same thing, one atom of chlorine multiplied by its mass, and then for oxygen, 3 atoms multiplied by its mass. Now I do want to point out the masses that you are seeing on this slide might differ slightly by that last digit, depending on what periodic table you're using. So some periodic tables only go out to 2 decimal places and some go out further. So the slight differences will still get you the correct answer. So calculating this all out, we get 84.455 grams per mole for the molecular weight of HClO3. Last problem, what is the molecular weight of C5H10O5? So this is a big one, right? There are 5 carbon atoms, 10 oxygen atoms, and 5 oxygen atoms. Or sorry, 10 hydrogen atoms and 5 oxygen atoms. So to calculate this one, you would find the masses of each element present multiplied by the number of atoms of each, and then add them all together. So here we have it all laid out, not going in the same order, unfortunately, as above. So it looks like they started with hydrogen here. So 10 atoms of hydrogen multiplied by the molecular weight, 5 of carbon, and then 5 of oxygen. When you add it all together, you should get somewhere in this range, depending what periodic table you used, of 150.13 grams per mole. Chemical reactions. So what are chemical reactions? Chemical reactions occur when chemical bonds between atoms are broken or formed. So you think about it, coming to lab, you mix 2 chemicals together, you get new chemicals out, right? So bonds are broken, new bonds are formed, rearrangement occurs. So chemical reactions contain two general components: the reactants, being the components that are mixed together. So those are the ones that are going to be put in the flask or the beaker or whatever container you're mixing them in. So they're the ones that are going to undergo the change during the reaction. And then, of course, the products, which is what you get out. That's what's formed at the very end, what you isolate, what your desire is. So when we're looking at chemical reactions, we always have the reactants on the left-hand side with an arrow pointing to the products. We represent chemical reactions by using chemical equations. So in this particular chemical equation, our reactants are going to be hydrogen gas and oxygen gas. We then have an arrow pointing to the product, which is water. So let's look at a few features of chemical equations. First off, these little subscripts in parentheses after each one, what do those represent? Those are representing the physical states of the reactants and products in the chemical equation itself. So whenever you see a little S after an element or compound, it means that it was added in a solid form. So we actually took or weighed out solid reactant and added it to the flask. Whenever you see the letter L, that stands for liquid. Now, it's not all liquids that you will be using in lab or in life. The L is only for a pure liquid. So remember when we talked about pure substances back in chapter 1, that means it was just one element or one compound. Okay, so when we're talking about a pure liquid, it's going to be a pure compound such as water, as you can see in the example above. The water has an L by it. It's saying it's water with nothing dissolved in it. So pure water. Now, you might also see, and will often see in lab, the term AQ after a compound. So what does AQ mean? Well, it stands for aqueous, but what it means for us in lab is that it's a solid that has been dissolved in water. So it isn't a liquid form that we're adding it, but it's not pure water, or it's not a pure liquid by itself. It's actually a liquid, in this case water, with a solid dissolved in it. Last but not least, we have G, which just means that it was added in a gaseous form. So in the example above, we had hydrogen gas and oxygen gas being added together to form pure liquid water. Now you'll also notice that there are numbers in front of some of the elements or compounds. These numbers we'll refer to as coefficients. So why are those numbers there? Those numbers are there because whenever we're doing a chemical reaction or representing a chemical equation, we want to make sure that that equation is balanced. So what does balanced mean? It means that there are the same amount of atoms on the reactant side as there are on the product side. So for instance, on the reactant side, if we were to have 4 atoms of hydrogen, we want to make sure that we have 4 atoms of hydrogen on the product side as well. Because whenever we do reactions, we don't lose material. It doesn't just disappear into thin air, right? It's just rearranged into new forms. It's that law of conservation of mass. It's very similar. We're not losing any mass, it's just being converted into different forms. When we balance chemical reactions, which we'll look at a little bit later in this section, we want to make sure that the molecular formulas remain constant. And then, as I said before, the atom count needs to be the same on both sides of the equation. So in the case above, how do I know that the atom count is the same on both sides of the equation? Well, in order to figure out the atom count, we take the coefficient that's in front of each element or compound and we multiply it by the subscript on that element or compound. So when I do it for hydrogen, I would be doing 2 times 2, which gives me 4 hydrogen atoms. Going over to the product side, I'm going to be doing the same thing for hydrogen to make sure that the atom count's the same. So I take the coefficient that's in front of water, because it's telling me there are 2 water molecules, and I multiply it by the subscript that's after hydrogen, which in this case is 2. 2 times 2 gives me 4 hydrogens. So my hydrogen atom count is the same, meaning the hydrogens are balanced. Now looking at the oxygens on the reactant side, there is no coefficient in front of that O2, so we assume the coefficient is just 1. So taking the coefficient of 1 multiplied by the subscript of 2, that gives us 2 oxygen atoms. Moving to the product side to see if the oxygen count is the same, we take the coefficient in front of water, which is 2, multiply it by the subscript after oxygen. Since there isn't one, we assume the subscript is 1. So that gives us 2 times 1 for 2 oxygen atoms. So this chemical reaction, this chemical equation is indeed balanced. So let's dive a little deeper into exactly how we balance an equation. So here we have an already balanced equation, and we can figure that out by doing the atom count. So I have the process written out here. To do the atom count, you want to take the coefficient that's in front of each element or compound and multiply it by the subscript. And you do that on both the reactant side and the product side to make sure there are the same amounts and types of atoms on both sides. So the work is shown below. You can see there are 4 aluminum atoms on the reactant side. When you take the coefficient times the subscript on the product side for aluminum, you also get 4 atoms of aluminum. For oxygen, you take the coefficient of 3 on the reactant side, multiply it by the subscript of 2 after oxygen, and you get a total of 6 oxygen atoms. Going over to the product side, you take the 2 that's in front of the aluminum oxide compound, and you multiply it by the subscript of 3 on the oxygen atom itself to get 6 oxygen atoms. So it looks like the atom count is the same on both sides. When you are balancing an equation on your own, so if it's not already balanced and you need to balance it, the coefficients is the only thing that can be changed to balance the reaction. So the number in front of the elements or compounds are the only things you can change to balance the equation. The subscripts cannot be changed. So those numbers in red, you cannot change the subscripts. If you change the subscript, you're changing the compound itself. You are now making a new compound, so you can't do that. What you can do is you can change the amount of the compound that's already in there by adding more of it. That's what the coefficients represent. The subscripts, you're going to be changing the compound itself. So be very careful with that. The next 2 slides are some examples and practice for balancing chemical equations. Now, trying to show how to balance and go back and forth between the reactant and product side on a PowerPoint video is quite difficult. So I'm going to leave this here for you to try to solve on your own. I've included a short balancing YouTube video in the email that I sent out to you. So you can watch that to see how you start from scratch to balance a chemical reaction, and then come back and try these examples on your own to see how it goes. Now, I will give you a hint. When you're balancing equations such as this, whenever you have the same element in more than one spot, so what I mean by that, in this case on the product side, notice you have oxygen here in the compound carbon dioxide, and you also have oxygen here in the compound of water. So if you have an element such as oxygen in 2 different places on one side of the equation, balance that element last. It's going to save you a lot of trouble because usually it'll balance itself out after you balance the remaining elements. So here is the answer for this one. So it's important to make a list of the elements present, and then you just go back and forth doing the atom count, adding coefficients until it is balanced. So to balance this one, you need a ratio of 1 to 3 to 2 to 2. So those are the coefficients that should be in front. For instance, for this 1, if you were to omit that 1, that's fine, because you don't need a coefficient there. If there is no coefficient present, we just assume it's a 1 anyway. So here are 2 more practice problems that you can try on your own. So the first one is taking nitrogen gas and hydrogen gas to form ammonia, or nitrogen trihydride if we're naming it systematically, as we learned with covalent compounds. So the first step in balancing, as you probably saw from the video, is to make a list of all the elements present and then how many are currently present based off of the subscripts given after the element symbol. Once you have that done, then you start adding coefficients to balance so that you get the atom count the same on both sides of the equation. So you'll notice for nitrogen, for instance, since there's a subscript of 2, that means there are 2 nitrogen atoms. Hydrogen, same thing. Now, when you're looking at these, you can tell that the nitrogen and hydrogens are not balanced, right? On the product side, we have 1 nitrogen. On the reactant side, we have 2. So you then need to add coefficients going back and forth until you get the same on both sides. When doing that, you end up getting an answer or a ratio of 1 to 3 to 2. So 1 nitrogen gas molecule, 3 hydrogen gas molecules to produce 2 ammonia compounds. Looking at the next problem, balancing this equation, you can notice that this time we actually have polyatomics. So different than they have shown on these slides, whenever you have a polyatomic, it can be very, very useful. If the polyatomic is the same on both the reactant and product side, do yourself a favor and do not split it up, keep it together. So what I mean by that is this carbonate ion, for instance, it stays together on both the reactant and product side. So looking at this, I can tell that there is 1 carbonate on both sides. So I can keep those CO3s together, just like I can with the nitrate, the NO3s. Doing that's going to save you a lot of trouble, especially when you're trying to balance those oxygens. So once you go through the process, this is the ratio that you would get. Now that we've learned about chemical equations and some of their features and how to balance a chemical equation, let's look at some common types of chemical reactions. The first one we're going to explore is combination reactions, also referred to as synthesis. So what exactly is a combination reaction? And how do you tell just by looking at the chemical equation itself? Well, combination reactions will have 2 or more reactants. So in the case of this reaction scheme, there's just 2 reactants represented by the letters A and B. Those 2 reactants combined, hence the term combination reaction, to form 1 product. So looking off to the right here, the atoms are represented. So we have 1 A atom and 1 B atom combining, so they're forming a bond to form 1 final compound. Some examples of combination reactions are below. So the formation of water would be 1, because we have 2 hydrogen gas compounds and 1 oxygen gas compound forming 2 water compounds. Ammonia, same thing. We have nitrogen gas and hydrogen gas combining to form ammonia. Next is decomposition reactions. So these are the opposite direction of those combination reactions. So in decomposition reactions, you're going to see just 1 reactant, which will be a compound. And what happens to that 1 reactant is it actually breaks apart, so bonds are being broken, to form 2 or more products. So opposite. Some examples. We have 3 different ones shown here. You'll notice they have names: thermal decomposition, electrical, and photolysis. You don't need to know the beginning terms, the difference between thermal, electrical, and photolysis. You just need to know or be able to recognize when given these chemical equations that they are indeed decomposition reactions. And you can tell that by seeing that there's only one reactant. I know there are 2 compounds, or 2 molecules, I should say, of this particular compound, but it doesn't matter. There could be 5 molecules. The important thing is that only one type of compound is present on the reactant side. So we have one type of compound breaking apart into 2 different products. In this case, potassium chloride and oxygen gas. The second example, we have one type of compound present here, so aluminum oxide, decomposing or breaking apart into aluminum and oxygen. Now the last one looks like we have peroxide here. So 2 molecules of peroxide are decomposing or breaking apart to form water and oxygen. So one type of reactant breaking apart into 2 or more products. That's the definition of a decomposition reaction. Single displacement reactions are next. They are sometimes referred to as single replacement instead of displacement, so just know those terms are interchangeable, replacement and displacement. So the general reaction scheme for these, as you'll see below, we have one compound. So here we know it's a compound because we have atom A with a bond to atom B. So we have one compound reacting with an element by itself, in this case, element C. So what happens in a single displacement reaction is that atom C is going to displace one of the atoms in the compound. So it looks like, in this case, atom C is displaced or replacing atom B to form a new product where A is now attached to C instead of B in the product side. Since C replaced B, now B is an element by itself on the product. So below are some examples of this. The first one being a redox reaction, and we'll talk more about redox reactions in later chapters, but most redox reactions are single displacement reactions. So you can see in this example, we have copper 2 sulfate. If you remember from naming, since copper is a transition metal, you need the Roman numerals after representing its oxidation number. So copper 2 sulfate reacting with zinc. So copper 2 sulfate, that's the compound, right? Copper with a sulfate ion. Now zinc is the element by itself. So what's going to happen here is zinc is going to take the place of copper. Now how do I know that zinc is taking the place of copper and not the sulfate? Well, because a metal always replaces a metal. Or to be more specific, a cation, which zinc would be a cation once it's in a compound, replaces another cation. So once zinc kicks copper out, that leaves copper by itself on the product side, and now zinc is in a compound with the sulfate, zinc 2 sulfate. Now let's look at this halogen example below. We have chlorine gas, which is an element by itself. I know it has this 2 beside it, but remember, chlorine is one of those diatomic elements in nature, meaning that chlorine never exists by itself. So there's never one atom of chlorine just floating around in the air. It's too unstable. So what it does is it pairs up with another chlorine atom to stabilize itself. So Cl2 is referred to as a diatomic element. So it is an element by itself, even though there's 2 present. So we have a chlorine element by itself reacting with a compound. In this case, we have potassium iodide. It's a good time to practice your naming. So now what's going to happen is, since chlorine is a halogen and likes to form an anion, a negatively charged ion when in a compound, it's going to replace the anion or the negatively charged compound. So it's going to replace iodine in this case. So when chlorine replaces iodine, it kicks it out, leaving iodine now by itself. And notice iodine is a polyatomic, or not a polyatomic, excuse me, a diatomic. That's why it has the subscript of 2, because iodine is unstable. One iodine atom is unstable by itself, so it finds another iodine atom to pair up with. And then now chlorine is paired up with potassium to make potassium chloride. Next, we're going to look at how to tell if a single displacement reaction will occur or not. Because even though a reaction scheme is written down, it's not guaranteed that the reaction is going to go to completion. So how do we tell? Well, since a lot of the single displacement reactions we're going to be looking at are redox reactions, that's the example we're going to use to figure out if this reaction will take place or not. So the general rule is that a more active metal replaces a less active one. So in this reaction scheme, zinc is the metal, in this case, by itself. So as long as zinc is more active than the metal it's trying to replace, which in this case is copper, then the reaction will move forward. So how do we tell if zinc is more active than copper? The activity series of metals will help us figure that out. So you might recognize this table. It is one of the tables that you needed to put into your lab manual as one of the reference sheets. So what we do is we look for copper and zinc on this table. Finding copper looks like it's pretty low on the activity series, which is good in this case since that's the metal that is being replaced. Lower the better. Zinc is the metal that's trying to replace copper, and notice it is much higher on the activity series. Since it is higher on the activity series, that means yes, it will replace copper, because it means it's more active than copper and it can replace copper. So that's how we're going to be using that table. We will look at that table a lot more during lab and when we talk more in depth about redox reactions. The next type of reaction we're going to explore is double displacement reactions. For double displacement reactions, you'll notice that the reactants and the products are both compounds. So we have 2 compounds as the reactants, 2 compounds as the products. So what happens in a double displacement reaction is they actually switch partners. So I like to see double displacement reactions or describe double displacement reactions kind of like a dance. So if you think of ballroom dancing or any kind of dancing that needs partners, what happens when you are doing a dance class or dance partners is sometimes you switch partners, and that's exactly what they're doing in a double displacement reaction. The nice thing about double displacement reactions is they usually follow the same pattern as well. So you can see we have element A and element B together in a compound on the reactant side. We also have element C and element D together in a compound. Now what happens is the outer elements, in this case A and D, are going to combine to form one of the products, compound AD on the product side. And then the inner elements, in this case B and C, are going to combine to form the other product. Now this is almost always the case. The outer elements combine to form one product, the inner elements combine to form the other product. This is important because at some point, particularly in lab, you're going to have to predict the products of double displacement reactions. So it will be very helpful for you to know that the outer elements combine to form one of the products and the inner elements combine to form the other. So let's look at some specific reaction examples. For double displacement reactions, they can be broken down into 3 subcategories. One of them is a precipitation reaction. So precipitation reactions, how do you know if the double displacement reaction qualifies as a precipitation? Well, the word precipitation stands for precipitate, and a precipitate is the word for solid in chemistry. So that means that a solid is forming. So you should see a solid in one of the products. How do you know if a solid formed as one of the products? Well, you look at these little letters in parentheses that come after each element or compound. So remember the letter S stands for solid, so that means this particular example is a precipitation reaction because solid is one of the products. You'll also notice that the other letters are AQs. Those stand for aqueous. That's when we have a solid that is dissolved in water. The next specific reaction example for double displacement reactions is an acid-base neutralization reaction. So for an acid-base neutralization reaction, the properties are going to be, you're going to have an acid as one of your reactants. So in this case, we have HA representing the acid. And for this course, how do you know if it's an acid? Well, all the acids we're exploring for Chem 1 are going to start with hydrogen. We already named some acids, monatomic and polyatomic acids, and they all started with a hydrogen. The base is going to have an OH in it for this course because those are the only bases we're going to be looking at in this course. Keep in mind there are other types of bases. It's just not ones we're exploring in Chem 1. So reactants, acid, and a base. The products then are going to be a salt, and that's what XA is representing, and water, H2O. Notice water has an L by it because it's a pure water with nothing dissolved in it. The last type of specific reaction example is a gas-forming reaction. So just like with all double displacement reactions, we have two compounds on the reactant side switching partners. Notice we have the outer guys, B and A, teaming up to form one product, AB. And then the inner elements, C and D, pair up to form the other product, DC. But notice, how do we know it's gas forming? Because one of the products has a G by it, indicating it's a gas. Combustion reactions are reactions in which you have a fuel source, and the fuel sources that we will see will mainly be made up of just carbon and hydrogen. Some of them will also have oxygen in them, but carbon and hydrogen will definitely be present. So a fuel source reacting with pure oxygen. Remember, oxygen is one of those diatomics that likes to pair up with another oxygen atom to stabilize itself. The products are always going to be carbon dioxide and water every time. So if you see the products as carbon dioxide and water, and the reactants have oxygen and a fuel source in them, you can guarantee that it is a combustion reaction. Some specific examples are below. Burning car fuel is the first one where we have carbon and hydrogen, C8H18, being the fuel source, reacting with pure oxygen. A combustion reaction occurs to form the products carbon dioxide and water. Now notice the coefficients in front of these. Very, very large coefficients. So balancing combustion reactions can be very difficult because of the very large numbers included. So whenever you are balancing a combustion reaction, remember to balance the oxygens last. So why do you want to balance the oxygens last? Because in the products, oxygen is in two separate places. We have oxygen on the carbon dioxide, and we have oxygen in water. So save it for last. Hopefully it'll balance itself out and save you a lot of time and energy. Now the next example is burning sugar. So this example has the fuel source containing carbon, hydrogen, but also oxygen. And that's fine, that's still a fuel source. But notice the other reactant is still oxygen, just like it should be in all the other examples. Products, carbon dioxide, water. Let's look at an example. So what type of general reaction type are the following equations? So for general reaction type, we have 5 that we had covered so far. They are combination reactions, decomposition reactions, single displacement, double displacement, and combustion. So let's look at example number 1. In example number 1, we have zinc 2 carbonate, which is a compound, reacting with another compound, and it looks like what's happening is they're forming 2 new compounds. So this should be pretty straightforward to see that it is a double displacement reaction. And remember, for double displacement reactions, just for practice, it's always the outer 2 elements combining. So in this case, zinc and hydrogen, or sorry, not hydrogen, iodine, to form zinc 2 iodide. as one of the products, and then the inner two also combined. So we have the carbonate ion combining with hydrogen to form the other product. The next example, we have a compound made of carbon and hydrogen reacting with an element, oxygen. And the products are carbon dioxide and water. So what would that be? It's a combustion reaction because this C2H6 is the fuel source and it's combining with oxygen to cause a combustion reaction that will produce carbon dioxide and water. The last problem, we have just one reactant, and it looks like that one reactant is breaking up into two separate products. So whenever you have one reactant and two or more products, it is going to be decomposition. Next, we're going to look at what type of specific reaction are the following equations. So the word specific, these are not just the 5 main ones. These are also the subcategories. And we saw most of the subcategories with those double displacement reactions. So if you remember, the double displacement reactions had subcategories of precipitation, where a solid was formed, gas forming, where a gas was formed, but also acid-base neutralization, where acid and base were combined to form a salt and water. So let's look. The first one, we have HCl reacting with NaOH. So two compounds reacting to form two new compounds. So this looks like a double displacement reaction at first glance. Since it is double displacement and they're asking for specific reaction type, we need to dive a bit further. So looking more closely, is it a precipitation reaction? Well, for a precipitation reaction, we should see a solid forming for one of the products, and it looks like we have an aqueous and a liquid, so it's not precipitation. Gas forming was another type of double displacement reaction, but I don't see any gases that were formed as products either. So it must be neutralization. And looking at the reactants, that holds true because HCl is hydrochloric acid, NaOH is sodium hydroxide base, so we do have an acid and a base reacting together, and the products are formation of a salt, in this case sodium chloride salt, and water. So this would be a neutralization reaction for number 1. Now looking at number 2. For number 2, we have aluminum, an element by itself, reacting with oxygen, another element by itself. And it looks like they're forming just one product. So we have two reactants combining to form one product. So what type of reaction would that be? Well, number 2 then would be combination or synthesis reaction. So I'm going to highlight that in blue for number 2. Now let's look at number 3. Number 3, we have iron 3 chloride, if we're naming it correctly, with potassium hydroxide. So it looks like we have two compounds forming two new compounds for the products. So with that, we know it's a double displacement, but they asked for specific. So what type of specific reaction is it? Well, since it's double displacement, we know that the outer two elements, or polyatomics in this case, are going to combine. So we have iron combining with the polyatomic hydroxide to form iron 3 hydroxide on the product side. And then we have the inner two, potassium and chlorine, combining to form potassium chloride. Now, it's not a neutralization reaction because we don't have an acid as one of the reactants and we don't have water as one of the products. Is it a precipitation reaction? Well, I do see an S for solid after the iron 3 hydroxide, so since a solid formed, I would call this precipitation. So precipitation reaction for number 3. Now let's look at some definitions. So we're going to look at solutions and solvation. So what exactly is a solution? We've already looked at what a solution is. Whenever we see an AQ in any of those chemical reactions that we've been looking at, that is a solution because what the AQ stands for is aqueous. And aqueous means that there was a solid dissolved in water. making a solution. So a solution is made up of two or more parts, a solvent and a solute. So a solvent is going to be the substance in greater amount. So in the example I just described, that would be the water that dissolved the solid, because the water would be present in a larger amount. Now the solute in the example I just said, the substance in lesser amount would be the solid that I dissolved. Now with solutions, we have several different types of solutions depending upon what type of solute was added. So the types of solutes that we're going to explore are first going to be an electrolyte. So electrolytes are solutes that dissolve in the water and form ions in the water. And that's the example that we have shown in the picture. So this big cube guy here with all the pluses and minuses stacked very nicely, that is going to be the solid, the ionic solid. When that ionic solid is added to water, what happens to it is it separates out into its ions. And that's what we are seeing here with these negatives and these positives. So they separate into their ions and are surrounded by water molecules. They make electrolytes since there are now charged particles in the solution, and those charged particles can then conduct electricity. So lots of properties with electrolytes in solution. So it's always ionic compounds that separate into their ions and can conduct electricity. Next, we're going to look at non-electrolytes. Non-electrolytes then are going to be covalent compounds. So remember, covalent compounds shared electrons. So since they're sharing electrons, there's no charged particles. So they're not going to separate into their ions once they're dissolved in solution. And since they don't form charged particles, they also cannot conduct electricity. And if you remember right, covalent compounds are compounds that are made up of just nonmetals. So that's how you can tell if it's going to form a non-electrolyte. If a covalent compound is dissolved, meaning a compound with nonmetals. The other types of solutes that we'll see will be acids and bases, but we're going to focus on the top two. So looking more closely at electrolytes versus non-electrolytes. What would make a strong electrolyte? So what would make a strong electrolyte would be a compound that completely ionizes in solution and strongly conducts electricity. So that is going to be the middle picture here of KCl, potassium chloride. So potassium chloride is an ionic compound made up of potassium metal and chlorine, which is a nonmetal. So since it's made up of charged particles, when it dissolves in water, it's going to dissociate completely into its ions. That's why we see little plus ions and little minus ions in solution. Due to those charged particles, it can therefore conduct electricity, and that's why we see the brightest light bulb. For a weak electrolyte, an example of a weak electrolyte would be this acidic acid solution. So weak electrolytes are going to partially ionize. That's why you see some neutral compounds that are still together that have not ionized or separated into their elements or atoms. But you also see a few charged particles. So partially ionized, not completely. So it still can conduct electricity since there are charged particles in solution. There's just not as many as there are in a strong electrolyte. So we see a weaker light bulb or poorly conducted electricity. The last one will be the non-electrolytes. So non-electrolytes do not ionize at all. So no charged particles in solution, meaning they cannot conduct electricity. The example here is ethanol, which is a covalent compound made up of carbon, hydrogen, and oxygen. So all nonmetals that do not dissociate when dissolved in water, meaning no electricity, so light bulb does not light up. Let's apply what we just learned to an example. Which of the following, when dissolved in water, would create a bright light or conduct electricity? So kind of ignore the bright light part. Doesn't matter how bright the light is. They're just seeing, will any of these conduct electricity? So how do we tell? Well, if it's ionic, having charged particles, then yes, it will conduct electricity. If it's covalent, made up of all nonmetals and does not dissociate into charged components, it will not conduct electricity. So let's look at number one. Number 1, magnesium chloride. Magnesium is an alkaline earth metal. Chlorine is a halogen, a nonmetal. So we have a metal with a nonmetal, which means it's ionic. If it's ionic, it will separate into its charged particles, magnesium with a +2 charge and chlorine with a -1 charge. So yes, it will conduct electricity. Next, we have ammonia, or if we're naming it systematically, it would be nitrogen trihydride. Nitrogen and hydrogen are both nonmetals, making this a covalent compound, so it would share electrons and not form charges, meaning it could not conduct electricity, so it would be a big no. Zinc 2 sulfate. So zinc is a metal, it's a transition metal with a +2 charge. SO4 is a polyatomic, hopefully that you've memorized from the polyatomic table. It's sulfate with a -2 charge. So since this compound is made up of charged components, it's ionic, and it will dissociate when dissolved in water into charged components that can conduct electricity. So a big yes. Last but not least, we have sugar. Sugar made up of carbon, hydrogen, oxygen. All of those are not metals, making it a covalent compound. And we would say no, it does not conduct electricity.